stupid woman. What?
I'm joy. This is sadness. That's anger.
What?
This is disgust. And that's fear. We're Riley's emotions. These are Riley's memories. They're mostly happy, you'll notice, not to brag.
I wanted to maybe hold one.
What happened? Sadness?
She did something to the memory.
Is everything okay?
I don't know.
Change it back, Joy.
Trying.
Joy, no,
Let
wait.
go.
The core memories. Can I say that curse word now?
What do we do now?
Nothing's working. Why isn't it working?
We have a major problem.
Oh, I wish Joy was here.
We can fix this. We just have to get back to headquarters.
That's long-term memory. You could get lost in there.
Think positive.
Okay, I'm positive you will get lost in there.
What was that?
Well, good afternoon, everyone. So we did a little bit of a change for today's opening. Well, usually I would play an opening video, which you probably already tired about it since you have been watching like 10 times of it. And I promise you, I will give you a new one in the next lecture. But for this transition, I especially put out the clips from Inside Out, which is one of my favorite movie that from Disney and Pixar, and to make sure that they don't sue me for like putting their trailers before my lecture. So I just want to say, like, if you haven't seen it or if you want to watch it again, well, Disney Plus, they have it, so go ahead and do it. And through the songs that we play before the lecture, which is also important as part of my lecture, because I really like you guys to encourage you guys to come in the lecture on time. So that's why I have the test question saying that, well, which of the song we didn't play before. And actually, I never repeat the same song. So if you hear that I play Memory today, you know that's probably not the right answer for your midterm. So through the setup of Inside Out and the song called Memories, is probably not too hard to guess about. Our topics today is all about memories. So before we start, it's always good to let you guys know where we are from and why we are here. And one of the very important thing is that, well, the big picture of computer architecture is that every computer, no matter how big, how small, how expensive, how low, how cheap, they are all von-Neumann computer architecture in a way that your computer contains processor, storage, memory, and needless to say, like the process of loading a program into the memory, and your processor will fetch instruction from the memory, fetch data, or update data to the memory. So as you can see, right, this processor, memory, storage, they are very important, especially the processor and memory part, because for the storage, once we get the stuff ready in the memory, it's off the hook. But processor and memory, they are closely related, they are closely tied together. And before midterm, we spend most of our time talking about the processor design. And now we are done with the midterm, and I believe you guys should have sufficient amount of knowledge to move on. So let's look at the other important part in our von Neumann architecture, that's the memory. So, so previously in the first lecture, we mentioned the performance of the processor and memory. Initially, they match. However, because the technology evolution keeps scaling the performance of processors thanks to Moore's law, and we use the additional circuits and to implement pipelining to make the processor speed a lot faster than it was in early 80s. However, on the other side for the memory, because for memory, we just want it to be big in terms of seeking for better performance. So it turns out that, well, the memory and the processor and memory companies, they are not the same set of companies. Well, Intel started with a memory company, but their memory business never success. So they turned out to become a processor only company. Some of you might argue that Intel still have the memory business right now, but that's actually, I would say they are selling the technology for Micron. So that's the Intel business. Excuse me. However, on the memory side, those memory companies, like ones I mentioned, like Micron or Toshiba or Samsung, they all focus on how to improve the capacity of your memory. So it turns out that the performance gap is really huge right now. So here I would like to give you an idea about what's the performance of modern DRAM. As you can see, for the for even with the latest DDR4 DRAM technology, even if we don't need to pre-charge, well, so at this point, I'm not asking you to figure out what's pre-charge, but you can see like even without pre-charge, which is an additional stage before you can access the content in your memory, even though it's already pre-charged, you still need to take 26 nanoseconds. So if you remember for 1 gigahertz processor, your cycle time is 1 nanosecond. So it means that, well, you need to spend at least 26 cycles for every memory access. And don't forget, for you need to access both instruction and data, right? So if you have a code like this, we know, well, it's not going to work very well because you see there are data dependency depend on this data index. So that's why for this part, because the data dependency is really bad. So it's hard to parallelize it through pipeline. So it turns out that for these pieces of a code, the right-hand side is faster because for the since this instruction is hard, this set of instructions, they are hard to pipeline. So if you can use instructions that has shorter CPI, you probably get performance benefits, right? So that's why for this version, B is a winner instead of an A, because this is a code that's hard to pipeline. Okay, so now I want to ask you, like, okay, so we just learned that the memory is so slow. So let's say, like, if you have a memory like this, and if your computer, if your in your processor is like this, like, what's the average CPI for running instructions? All right, let's wrap up in 15 seconds. Oops, it's not moving. All right, so everybody has a vote. So so looks like I think we really need some discussion among you guys. So I just sent out the questions through the group chat. So please right now spend some of your time try to discuss with your friends in detail, because it's really important that you understand this topic. And I just want to say you really need to discuss, because from what I saw from your poll, only one of you in a class get the answer right. So please discuss with your friends in detail, carefully. Go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I need some representative to tell me what your group is thinking about. Okay, so I have Japong, I have Harris. Okay, so let's invite both of you to speak up for your group.
Our group chose B.
Same here.
Okay, so how do you derive your answer?
So given that the process runs at 2 gigahertz, the cycle time will be half nanoseconds.
Right?
And then the memory access will take 52 cycles.
Okay, so 52 cycle. So how do you do that? How do you calculate it?
26 nanoseconds divided by half nanoseconds per.
No, I mean, how do you get a CPI?
Oh, that's like 52 times 0.3 plus 0.7.
So 52 plus, times what?
0.3
30%?
Mm-hmm.
plus 70%.
And
Plus 70%.
plus 70%?
Yeah.
Why?
Because we assume the computer has perfect. We assume it's like the rest of the instruction is like one CPI.
Yeah, so the thing is that, okay, so even though you don't access memory, right, the CPI is 1. Right, so this will be the additional overhead, so you should plus 1. Right? But
Yeah.
is that right?
Well, no, it would be plus 1 times 70% because it would be plus
No,
1
you
for.
cannot time 70%. You have to time 100%.
Why is that then?
Because the perfect memory means there is no latency in access memory, right? And even though you have to spend 1 cycle per instruction, now you have to additionally pay 26 nanoseconds to access the memory. So it will be 50% times 30% plus. Okay, so if you really want, if you really like your 70% to be here, then you will be 50% times 30% plus 1 times 30% plus 1 times 70%.
Oh, when you say perfect memory, if the computer has perfect memory, we're not implying that the DDR4 is somehow replacing that perfect memory. Like, oh, the computer has perfect memory, this is the ideal case, but now in the real case of DDR4, we're assuming there's a latency, so now what's the CPI?
Yeah, okay. But even though I don't think it will significantly change your answer, right? Because it's just a difference by 1.
Yes, it's not going to.
But right now I'm telling both of you guys are both wrong.
Okay.
Why?
I don't know.
So have you guys ever pay attention to the slides that I present before the lecture? Well, before the real, well, you guys always thinking about like the recap part is not the lecture, but actually that's also important because that set up the whole stage for the rest of the lecture, right? So tell me about what's a von Neumann architecture.
Well, what, the idea of the processor, the memory, and was storage, and the idea that by having memory containing both instructions and data which feed into the processor, and then the memory itself has instructions and data that come from the storage, you allow a computer to have the capacity to run different programs.
Right, okay. What are the programs? What's a program?
A series of instructions that manipulate data in somehow.
Okay, where are those instructions?
It would be in memory.
Did you include the time you have to fetch the memory? Fetch instruction from the memory?
Is that not included in the CPI in perfect memory? I mean, I'm assuming the answer is no, but I'm just confused as to why that's not the case.
Because you have to put your instruction in DDR4 as well.
Oh, right.
Right? See, when I draw this graph, did I separate? Did I put the instruction and the data in different memory? Did I put them in different memory? No, they are together.
No.
So if you have to pay the overhead of access data, you have to also pay the overhead of accessing instructions, right? So, oh, there's another question. Sorry about that. So if you look at that, right, then what it turns out is that, right, let's do the math together right now, right? So it turns out that the answer is E. As you can see from the result that I show you, only 2 of them get it right. And the reason is that if there's no memory get involved, the base CPI is 1, right? So this is the perfect case. However, the world is not perfect. So we have 52 cycles because your memory access latency is 26 nanoseconds, right? So it's equivalent to 52 cycles, right? So every instruction need to fetch instruction from the instruction memory. 100% of them has to pay the 52 cycle to fetch your instruction, get it ready into the processor look over it and figure out, wow, this is a data memory access instruction. So 30% of them will be the case. So average CPI will be 69 cycles. Did you get it?
Right. So essentially, for all instructions, you're going to have essentially effective CPI of 53. But
Yep.
then on top of that, for 30% of the instructions, you're also going to have an additional CPI, well, 53 plus 52, which.
Right, exactly.
Right.
So and thanks a lot. And actually, this is actually, well, so that's why I designed a problem like this, because that's exactly the answer I'm supposing you guys to answer. So thanks for you guys cooperation, because you did give the answer that I was expecting, right? So that's great. All right. So right now, I hope through this example, you completely understand the limitation of von Neumann architecture and why memory is so important, because every instruction is coming from the memory. Every instruction is coming from the memory. Data are also from the memory. So everything involved in memory, instruction fetch, memory stage, they all need to access memory, and every instruction need exactly instruction fetch. So that's 100%. 30% of instruction here, they need to access the memory. So that's why the 30% is like this, right? Okay. So now you will have the question. Okay, if this is our computer architecture, and look at the example that we have in the last 2 lectures. This is in a memory. This is the memory, right? If the memory is so slow and you have to pay additional overhead in accessing data, then these pieces of code, it's not going to be faster. So there must be something else. There must be something else that we are doing behind the scenes for programmers. So that's the topic we are going to talk about today. So in addition to DRAM, there are other memory technologies. So DRAM is the one that we use for main memory. And as you can see, the typical access time is 50 to 70 nanoseconds. However, because it's a lot faster than flash memory and magnetic disk, plus there are some other benefits. So DRAM is still the mainstream technology that we use to build our main memory in computer system. However, there's another technology called SRAM. The typical access time, as you can see, is aligned with your processor speed. However, it's 20 times or even more expensive than your DRAM. So Harry's, what question do you have?
So in the book, it mentions very briefly the concept that DRAM, essentially each bit is stored in a capacitor and it has to be constantly refreshed. That's why it's dynamic, right? But then it does a very, even in the appendix, it does a very like hand wavy sort of thing of, yeah, SRAM and Flash, they both, SRAM uses latches and then Flash memory structures, it uses more advanced gates to make sure it's non-volatile. Is that, it's very not detailed of an explanation. I was
Well,
hoping
and I tell you why.
you,
Because that's what your CSE140 professor should tell you, not our class, right? So for CSE141, your duty is to know, okay, there are these technologies. SRAM is faster, but more expensive. DRAM is faster than flash memory, more expensive than flash, but it's already reached a point that we can accept it as the main memory, right? But how they are made, what their characteristic looks like, and what kind of gate level stuff, I think that's the duty of CSE140, right? And as you can observe in my class, I never mentioned gate level stuff because I think it's not necessary for you guys to know here. And you are supposed to know this already in CSE140. All right?
All right.
All right. So, okay, hopefully that will be great. So now you know, well, if you have good understanding about CSE 140, and even though you don't know, that's okay. Just need to remember what we draw in this chart is that the SRAM is faster than DRAM, but more expensive. So we are not going to use SRAM to replace DRAM. So what are we doing? So this, instead of like replacing the complete main memory with SRAM, this is what we do. We build something called memory hierarchy. So the concept of memory hierarchy is this. So far you see the processor, the DRAM, the storage, which is the three main parts of the von Neumann architecture. And usually your processor is running at a cycle time less than 1 nanosecond. And your DRAM is running at the cycle time for tens of nanoseconds. And your storage is usually in a level of microseconds if it's powered by flash. And if it's a hard disk drive, then it's usually milliseconds. So, and in terms of a capacity, the fastest memory technology you can find is probably registers. And but because register is large, even though it's very fast, but you can only build like 30 to 60 words in your processor. And for DRAM, usually you can use you can usually buy like gigabytes of memory within about like right now I think you can buy about like 32 gigabyte for $150, right? So it's okay. And storage, like for $150 you can get like probably 1 tera or 2 terabyte of an SSD. Debbie, question?
Oh, what's the difference between the processor and processor core? Meaning, like, what's in the processor?
Okay, so the reason why I draw this is because processor, there are something else here. And let me show you the magic. So that's why I have this, and because we have the animation here. So, okay, so right now processor, if you just make your processor like this, right, there's a huge gap between your processor speed and DRAM, right? So what we end up doing is that we change the processor core, processor to contain not only the processor cores, but also the SRAM as the cache. Debbie, does that answer your question now?
Yeah, thank you.
Okay, right. So what's the good thing about putting the SRAM? Well, so right now in typical memory hierarchy, we put a few SRAM, which is usually like kilobytes to megabytes of the data storage, and it takes just a few nanoseconds to fetch. So if you remember the movie that we just played before the lecture, it's Inside Out, right? So the core memory, you can consider them as the registers. So whenever Riley's emotion wants to do something, they can only fetch her memory from the core memory. That's exactly like what the processor is doing. ALUs, they can only access the registers. And whenever the core memory is not containing the stuff that we need, they have to go back to the short-term memory that's behind their control center. So that short-term memory is essentially the SRAM, because if you want to fetch data from a short-term memory, you just need to take a few seconds to walk there, put it into the core memory, and you are done. So imagine you are working on a project, or say you are working on a midterm. We say it's an open book, right? So that's why some of you guys were asking, okay, can I put my iPad beside my computer? Because you know, if you do this, that will save a lot of your time to access the content on the iPad instead of some other room in your apartment or in your home, right? So that basic idea is like cache. Now, what about DRAM? So DRAM is slower. So it's like the long-term memory in inside out that you need to spend a lot more time to get the result, to get the content from there. And for storage, if you remember the garbage collection place in the movie, right, which take them the whole movie to find out where Raleigh's happy memory is, right, then that's even a lot slower. So that's a memory hierarchy we built. And our goal is that, well, if we can get sufficient amount of stuff, useful stuff in the SRAM, most of the time, we don't need to go to the long-term memory. We don't need to go to this garbage place, right? And apparently, why they are getting lost there, because it's such a place that they are not familiar with, right? So that's the concept of memory hierarchy. So right now, I'm asking you a question. If we know that you have a memory hierarchy, and given the configuration, that the same configuration plus the memory hierarchy, how can that help your performance? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so looks like, well, the answer looks like a normal distribution in some sense, like well, evenly distribution. So definitely we need some discussion among you guys. So I just sent out the file through the chat. So just open the file that I sent out first and then start group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's see. This is what you guys think after discussion. So from evenly distribution to one answer that's slightly like half shy. So can I have some of you share what your group is thinking about and why does that make you feel like, well, the answer that I'm choosing is right? Okay, Harry, you are the king of the world.
Well, our group could not come up with a consensus whatsoever, but
okay,
the
but
answer.
What are the interesting discussions you guys have?
We were stuck between 32 and 4, and really what it all hinged on was.
So why?
Okay, why? Because it all hinged on what does the 90% cover? Does the 90% cover all of the loading and instructions of all the data and instructions that's bound for every single instruction?
What is said?
Desired instruction, data, and instructions. So I assume that means all of them, right? Not just load, store,
all of them, both of them.
Okay.
So if that's the case, what do you guys think?
Well, then we would argue that it would be 4.
Okay, but how did you get that?
Oh, how did we get there? All right, so there's gonna be.
It's more important about how, right?
Okay. Well, then the equation would be 1 plus 0.9 times 1, because a latency of 0.5 nanoseconds with 2 gigahertz is just 1 cycle, right?
Okay.
Plus 0.1. So now this is the 10% that's not covered in the SRAM. Times 0.3, although this was also heavily debated, times 52 cycles.
Wait. 0.1 times what?
Okay, so some of us in the group decided to multiply times 0.3 and 52 because we somehow wanted to incorporate the 30% of load store instructions, and some of us just left it at 0.1.
But should you do it?
I don't know.
Okay, so can we make it easy? Like, let's say like we calculate the instruction part and the data part separately.
Okay.
So for the instruction part, right, thinking about this, right? So 90%, well, so right now, let's say this part is, well, so let me use a different color. So let's say like for the blue part, it's about the instruction, right? So every instruction needs 1 cycle at least, right?
Mm-hmm.
And I would say like, okay, so for 10% of them, right? They need the additional cycles. Do you agree with that?
Yes.
Okay, so what's the additional cycles that is necessary?
It would be 52.
52, okay. So now, how about the data part?
The data part? Oh,
Yeah,
so for load store instructions, right? That would be
30%
30% of all instructions would require an additional 52. Oh my God.
Which is,
now,
well, but that is, well, no, the instruction part is already covered here, right?
Yeah, but then load store would have to access memory once more, right?
Right, so what's that once more?
Well, once more meaning there's a 90% chance that it's only going to have 1 cycle, and then a 10% chance that it's going to have 52.
Right, 52, right?
Mm-hmm.
So that's 1 plus, what's this? 5.2,
Mm-hmm.
right? This is already greater than 4.
Yeah.
And how about this part? This is going to be like about like 1.5 or something.
Yeah,
right?
somewhere along those lines.
So if you do the math right,
Mm-hmm.
here's the answer.
0.1.
This is the 10%, right? So if you do the math right, here's the answer. So if you iterate with me, you will figure out that, oh, it's like 7.76, right? See that?
So hold on, there's one. Okay, so there's 1 cycle for all instructions at least, right? And then
because that's the perfect CPI, right?
That's a perfect CPI. And then if we're accessing the data in the SRAM cache, then it's going to be 1 cycle on top of that, correct?
It's going to be, well, so if we got a latency, okay, so even though we have 1 more cycle, right? If you want to count that 1 cycle, it's still like 8.7.
Yeah, no, it wouldn't, but it might come into play later on, say on a test where it's free.
Right, but we can usually say the SRAM cache is part of the pipeline.
Oh,
because,
yeah.
Right, because that's why for this graph, right, we draw the SRAM cache, right, as part of the processor.
Mm-hmm.
Right,
so
because it's part of the pipeline.
Right, and so then all that's left is, all right, what about the 10%? Well, within the 10%, then of that 10%, there's always
You
going
have
to
to-
be 52, and then but there's on
Right.
top of that 32% that has an additional, and that's taken care of.
Right. So
Okay.
do you agree with me now?
Yes.
Okay, awesome. Thanks, Harris. You are our top performer for today. Okay, Albert. Albert.
Hi.
I
Sorry
saw
if
you are
this-
interning right now.
Yeah, I'm at work. Yeah. Yeah.
Okay.
Uh,
Okay. Question.
yeah. So sorry if this has already been answered, but where does the 52 come from?
So you have the memory 26 nanosecond, right? And your processor running at 2 gigahertz, which means that your cycle time is 0.5.
Yes.
Right?
Oh, so
So,
okay.
so 26 nanoseconds is 52 processor cycles.
Oh,
20
okay.
divided by 0.5, that's 52.
I see.
All right?
Okay. Thank you.
Okay, Yizi, do you have a question? What's your question?
Yeah, hi. So I'm not pretty sure if it's been already answered, but I just want to ask, like, so here we have the one on the leftmost for on the red equation here. So this is the this is mean that the perfect CPI is just one, right? So for
Right. So even though there's no like your memory is perfect, it's everything is completely integrated into the processor. Accessing memory doesn't incur additional overhead.
yeah,
That's one.
yeah, and then like 90 per the 10% of the things that still need to be done by the 26 nanoseconds, which is 52 cycles. But where is the 90%?
The 90%. The 90% here.
Yeah, I mean here is like 1 minus 90%. So
Right. So that's the 10%.
yeah, that's the 10%. And where is the other 90%?
There's no well, like, okay. So for so where's the other 90% is used here, right? Because 30% of the chance you are accessing your data, and there's still 10% of the time your data is not going to be in your SRAM cache.
Yeah.
Did you get that?
Yeah. Yeah, I think I get it. Thank you.
Okay, great. So for this question, I think right now you understand the concept. And well, a lot of you now might be curious about, like, okay, how big is my cache? So this is the computers that I have. So I have this computer at home. And well, if you run Windows, there's a tool called CPU-Z. It can tell you how, the spec of your processor. Like for my Ryzen 7 processor, which is the later, the earlier generation of the Ryzen processor from AMD, right? So it's an 8-core processor, but that's not the big thing here. What you can see here is that, wow, so for the cache, I have level 1 cache, level 2 cache, level 3 cache. And for Intel processor, I still have the level 1, level 2, level 3. So why do I have, so it's essentially that there are hierarchy within hierarchy, right? So they so you think, well, I just have the big hierarchy processor, SRAM, DRAM, but within the SRAM there are still level 1, level 2, level 3. So it's like, okay, you guys think like going to like working in a company, right? You have junior entry-level engineers, you have senior engineers, you have staff engineers, and then you think that's the 3 ranks, but it's actually not that, because like even for like junior engineer, there are level 1 engineers, level 2 engineers, level 3 engineers, level 4 engineers, right? And and when you become a senior engineer, there is still going to be another layer system like that, right? So the same thing in our computer architecture is that our processors are built in hierarchy with hierarchical caches. So what's the benefit of that? Can you go through this problem to evaluate what's the benefit of making your SRAM a hierarchical structure? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so it looks like we still need group discussion given the distribution of your answers. And I already sent out the question through the group to chat. So let's go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, after the discussion, it doesn't help that much. And actually, I think it's getting worse. So what if I have some of you share what your group is thinking about with us, and maybe we will figure out which part of your thoughts are not correct. It's not correct. All right, Harris.
Once again, it's not a consensus at all, but we'll go through the equation again.
Okay.
So the equation was 1 because it's the perfect memory, right?
Right.
Plus 0.9. Well, it depends if it's streamlined, right? But we're assuming to make our lives
well,
easier.
that's assuming it's a pipeline.
Right. That's not true with the pipeline?
Assume it's a pipeline. It's part of the pipeline.
All right. Then we're going to ignore that 0.9. All right. So we're going to say 1 times 0.1. All right. So this is all the stuff that is not captured within the first level, right?
Okay.
Well, now
so this is the, so we will say like 1 times like 1 minus 90%, right? So some of you will be clear where it is from, right?
Right. And now the second level, so 1
no,
times
what's the latency of the first level?
Latency is 1 cycle.
No, but what about this 10%? How much time we need to get this 10% from?
Oh, how much time you need for the 10%? Oh, assuming, but this part of the equation, we're not covering the stuff that's gotten in.
Okay, so what are you going to do now?
Okay, so now I was going to multiply it by 0.6 and what is it, times 10.
60% times 10. Why?
Why? Oh, no, not 10%, just 10 cycles. Because 60% of the instructions can be covered at the second level at 10 cycles. Plus, right, 1 minus 60, which would be covered in, it would have to go back to the DDR4. And so now here it would be 52 cycles, right?
No. So again, right? Look at this. So this is the memory hierarchy, right? So how do I know if something is in the label of memory? I have to look up first, right? So do you think the math is right if you just time 52 here?
I mean, how long would it take to look up something at the second level? It would be the latency.
You have to look up it for 10 cycles.
10 cycles.
After you access it for 10 cycles, you know it's not there. So you go down.
Right. So then it would have to be 62.
Or say, right, like just say like 10 plus 1 minus 60 times 52.
Yes.
Right? Okay. Then?
Well, now we have to consider the load store cases. So that would be, let's assume the load store is in the first level. That would be 1 times 1 minus 90%. Times 70%. Wait, no, this is 1 minus 90%. That would put us in the second level. Sorry. Let's go. Let's do it first level.
Okay. Okay. So maybe you should follow my way, right? So let me show.
Probably better idea.
All right. So this is how I got it, right? Oh. Oops.
Yes.
Well, okay. So look at this, right? So 1 plus 1 minus 90%, and 10 plus 1 times well, so those parts are similar as you do, right? The only thing is that for the second part, 30% of them are memory access instructions. And for those memory access instructions, if it's a hit in the first level cache, right? If it's if it's a hit in a second level cache, like 10 cycles, right? And if it's not found in a second level cache, you have to pay like 52 cycles, right?
So I have a question.
Sure.
What happens in the case that the data is located at the first level, but it's a load store instruction? Where is that covered in the
There's no penalty.
There is no penalty.
Yeah, given the latency is aligned with the pipeline speed.
Oh, okay. Right, because it's aligned, then we can assume that it's pipelined. All right.
Right. All right. So for this question, thanks Harris for your top performance today. So for this question, right, you can assume what's really about memory hierarchy is that, well, for the SRAM part, we further make them also hierarchical. So in your SRAM, there is also level 1, level 2, level 3. And as you can find from the previous question, the reason why we do that is because right now we can shrink the average CPI from 8 to 5, so or it's close to 4, so it's faster, right? So the only reason why we built multiple memory hierarchy, and the more hierarchy you have, the deeper the hierarchy you have, presumably, as you can see from our examples, is that it's going to be faster. So that's why we go deeper right now with level 1, level 2, and level 3, and they are all on chip. All right, so okay, so right now you might be curious about, okay, why adding the small SRAM cache would work, right? How come this idea would work? And the reason is because, well, this will work and because your code has locality. So what I want to ask you about is that what's locality and where are the locality coming from in your code? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so from what I learned from you guys, I do feel like we are in need of a group discussion, which I already sent out a question through the group chat. So right now, let's go ahead and do the discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you guys, this is the outcome. So looks like, well, C and E, they are both popular answers. So, well, so for those of you who chose C and E, okay, both of you agree some has temporal locality. Both of you agree that A has spatial locality. But for E, you think A additionally, some also additionally has spatial locality. So why? Well, can I have some of you share your thoughts? Okay, Byron. Okay, somebody else other than Harris.
So the reason why we think that sum has spatial locality is because that some index 0 through 10 are accessed at some point in the program. So if you kind of load that section, you're going to be using it quite often. I don't want to use often because that gets into temporal locality, but yeah.
Right. So here's the thing, right? So for spatial locality, like A1 through A, like 100,000, that's temporal spatial locality. And for some, it also has the spatial locality through 0 to 9, right? So there's no reason saying that, well, one data can only have one type of locality. And some is the case that we have both localities that you have data being reused and you also have data that's accessed in its neighbor, right? So the answer for this question would be E. And if you go back and look at the locality, the definition of a locality is probably not too difficult for you to understand why. Because the definition of spatial locality is that, and thanks, Byron, and the reason, the definition of spatial locality is that we tend to access data or instruction that's nearby. So if you look at the locality actually exists a lot in your code and data in a way that for your instructions, after you execute this one, the next one will be TC+4. And it's right next to each other. So that's spatial locality. For data, if you have a data structure like an array, you also have good spatial locality. And for temporal locality, it means that application would revisit the same thing again and again. So for code, if you have a loop, you are going to execute the same set of instructions again and again. And for data, if you have a shared variable that you need to update frequently, then or a table that you have to update frequently, the same data can be read and write many times. That's locality, right? And think about that. Well, let's set the code aside. Even for the data, many of your algorithm is designed in this way. So most of the time, your program, the big implication behind locality is that your program is just visiting a very small amount of data instructions within a given window. So we are not saying that the whole program is not visiting a larger amount of data. But what we are saying is that within a given period of time, your program is just visiting a very small amount of data instructions. So that's why the idea of cache would work. So this is the high level view of your cache. So if you don't have cache, what would happen is that if I want to load a word or say a byte from an address, then what I would be doing is that, okay, I gave you an address and then I would go to the big memory space like this, right? And this would take like tens of nanoseconds and or say like tens of CPU cycles, right? So that's the normal case. However, and after I'm done, I have to fetch the next word again, right? So that's what would happen if you have processor, if you only have processor in the DRAM. However, with an SRAM cache, our basic idea of the SRAM cache is that we want to capture the spatial locality. So instead of fetching data word by word, we just grab the whole chunk of data, which is called block, from the main memory whenever you need it. So let's say whenever I miss a word like number 9, then instead of just taking word number 9. The SRAM will logically partition the memory space into block. And then I fetch the whole block, which includes 9, 10, 9, A, B, C, this data into my memory location, into my SRAM cache, right? So in this way, the next time when you access the next word, let's say A, it will be directly served from the SRAM instead of DRAM. So first of all, to capture the spatial locality, the architecture of your SRAM would organize, logically partition your memory space into blocks, and we also stored or say like fetch data in the unit of blocks. That's how we address the spatial locality in your program using the SRAM. However, here's the question. How do I know? How do I look up my cache to tell what's the data I have? So here is how we do it. So whenever you need to load store something, right? You go to the specific block that you are interested and check if the tag here is exactly match the memory address that you are, the tag of your memory address that you are accessing. So let's say right now, if I have many blocks within the cache, I would attach a tag to each of the block. And the tag is standing for the prefix of its memory address. So let's say, and in addition to that, each block would have a dirty bit, a value bit, to let you know if the content in there is trustworthy or if the content there has been polluted. So let's say if right now I want to load data 0008, and given that I have a block like this has 16 bytes, you only need 4 bits as the block offset. So you can kick out the last digit from the hexadecimal, and you will figure out the prefix that will be used for tag would be 000. So given that, you separate the prefix part, and that's fine if there's any tag here match, any block with the tag matches the requesting tag. And it turns out that we find the zeros row has the stuff. And we are looking for block offset A. So we just redirect our bit line to the our mux to block offset A. So so you just output the data here and send it to the processor. So that's the whole process of accessing cache. Okay, Harris.
So I can understand why you would also have a valid bit for the cache. What's the purpose of having the dirty bit as well?
Okay, we will talk about this later. It's indicating if the data has been modified. Because, okay, so here's the thing, right? If you have modified something in the cache, that update is not presented in the lower level memory hierarchy or elsewhere. So the dirty bit is indicating that the cache is the only one who has the up-to-date data.
Thank you.
Okay. All right. So so that's the organization of, well, so but what if I have a different address? And let's say like this 404A, the same offset. However, if you separate the tag part is 404. And if you go to look that 404 in your cache tags, you will figure out it's not found. So you have to go to lower level memory hierarchy, right? So that's how the cache works. However, as you can imagine, if we organize our cache like this, then a big issue is that if I want to search for the matching tag, it's a table. And I have to do linear search. So it's an older algorithm, and everyone needs me to compare. So it's not fast enough. So instead of organizing the cache in this way, we have to figure out how to search things faster. And well, usually I would like to criticize what you have learned from CSE 100 and 101. However, there is indeed a data structure that's really useful to solve our current situation in minimizing our search time. And a lot of you might already think about that. That's called hash table. So what we want to do is that we should organize our cache architecture as a hash table in a way that when we want to figure out if something is indeed in a cache or not, let's just go to the hash, the entry, and check its tag. That's a basic idea. So here's what we built. So we want to have a hash-like structure. So let's say if I want to load 000A, I would have a block offset still because it indicates where the requesting word is in a block. However, I would additionally use one part of the memory address as the index and compare the tag within the index to see if it's consistent with the content, with the index that I'm requesting. And in this way, you always need to just search one or very few entries in a cache. And just compare the tag, you will know if it's a hit or miss instead of searching the whole cache. So that's the hash-like structure. And if it's a 404, I know I have to go to this entry because that's the only possible hash mapping of this entry. However, if it's not 40, I know this is not found. So that's the basic idea of a hash-like structure for the cache. However, you know, the biggest issue with hash is that there are collisions. So how can we avoid that? So in software, we can definitely have some more flexible data structure. But in hardware, the only thing we can do is that we make each hash entry to be able to contain multiple blocks. So what we end up doing nowadays is the weight associativity cache. So the basic idea of a weight associativity cache is that beyond the granularity called block, we organize blocks into sets. And whenever you have a memory address, we still partition the memory address into tag, offset, and set index. And we use the set index to find out which set contains your data. Use the block offset to figure out where in the cache block your data is. And for this example, because its set index is 0, 1, 0, that's equivalent to 2. So we go to the second set in the cache. And the tag part here is 0, 0, 0, 1, 0, 0, 0. And if you write it in hex, it's actually 0x10. And if you compare these two entries associated with this hash index, well, this is A1, so that's not equivalent. However, on the left-hand side is 1, 0. So your requesting word is indeed in the intersection of this set and this offset location. So what you will do is that I would compare the tag, and if they are equal, I know it's a hit, and if it's a hit, my mux would select the left-hand side word for output. Okay, I know this is what you think, and I have a better way for you to understand in the next lecture. But before we talk about that, right, please go through the slides that I presented today and try to give yourself some idea about how cache works. And now let's talk about, a lot of you were asking about how am I doing in the midterm? right? So, well, but before you leave the classroom, there are a few things. First of all, I want to let you know the reading quiz due tomorrow. And midterm average is 76, which is doing okay. And I think it's, well, I would say doing great. And again, a lot of you were asking about the standard deviation or whatever. I just want to tell you, and is there going to be a curve or not? I just want to tell you the final grades is decided by your overall grade. So a single item doesn't mean anything. So if you are curious about where are you in the class, you should go to Canvas and check your current overall score. And here's the rank, here's the list of the overall score. And as you can see, you guys are doing so great. So here's my current plan. I'm saying about my current plan is that if you guys keep maintaining the same performance and you guys are like cooperating as what you are as what you guys are doing so far, and keep participating in a class, like, and people shows up and people raise your hand whenever I ask a question, then this is what I'm planning to do, right? So if you are at this part, you are going to get an A+. And if you are at this part, you are going to get an A. If you are at this part, you are going to get an A-. If you are at this part, you are going to get a B+. If you are at this part, you are going to have a B. And some of you were worried about like, oh, is there a failure? Is there a fail or something? Well, one thing I want to let you know is that since I started teaching a class, I never failed a student who attended final. I never failed a student who attended final. I can testify this, I can swear, I never failed a student who attended the final. So if you are worried about if I'm going to pass or not, you are already, if you decided to take the final in the scheduled window of time, you already can pass the class. It's more about if I can get better. And I will tell you, if you try hard in the final, you will definitely get better, right? So, and again, if you don't trust me, at least you should trust CAPE, right? The course evaluation, and go back and look at my history starting from 2012. And you know, like we already give you the most generous grading across all the CSE 141. And if you cannot ace in this session, I don't think you can ace in any other session. Okay, so that's the message I want to give you. And the big thing here is that if you guys can keep working as what you are now, and some of you were worried about that and keeps like bumping me like emails or Piazza posts, I think that would just let me change my mind. All right. So other than that, I think we are good for today's lecture, and I will see you tomorrow. And don't forget, we will have a reading quiz due tomorrow before the lecture.